Okay, in this video, I'm going to demonstrate how you can run regression analysis through the general linear model univariate option in SPSS. Now, conventionally, when people run regression analysis through SPSS, they'll go through the regression module, go to linear, and they will basically just put their dependent variable in the dependent box, their independents in the independent box, and then select whatever other options they want to choose. Like they might select confidence intervals, part and partial correlations, collinearity diagnostics, and so forth. And so, here's an example where I'm just basically running a multiple regression with worry and self-efficacy as predictors of a variable called interest. This is the R-square value, adjusted R-square that you see right here. The f-test value of the f-test, and you can see that the model is statistically significant. We also get our unstandardized coefficients right here, as well as their standard errors, t-values and p-values, and so forth. So you can see we get a pretty good bit of information through the standard route. Now there is some information that you can't quite get through this route, and there are some additional options that are available if you go through the general linear model univariate route. So what we're going to do is click on this, and let me just kind of briefly note that I know that oftentimes when people are utilizing this particular approach, they're using it for the purposes of carrying out standard analysis of variance, where essentially you'll incorporate your continuous dependent variable and one or more factors that are included in the fixed factors box right here. And then if you're running an ANOVA, you would be adding in the covariates down here. But you can actually run the regression and get all the same results through this particular option. And in addition, we can also, there's some new options that are available to you where we can actually test for heteroskedasticity in terms of the residuals, and also maybe even even be able to carry out robust regression where we adjust the standard errors for heteroskedasticity. So that's really kind of the payoff of knowing this particular route right here. So to do this, what we're going to do is we're going to move our dependent variable from this model over to this box right here. And we'll also add in our independent variables from the previous regression into the covariates box. And just keep in mind that basically the regression model is is the general linear model. So there's nothing really different that's going on right here. Some of the presentation may look a little bit different, but we're going to get the same information, at least with respect to the least squares regression. So at this point, I'm going to go ahead and click on options, and then click on parameter estimates right here. Also, I can ask for effect size and so forth. So I'm going to actually stop right here. I'll show you some of these other things in a few minutes, but I'm going to stop right here and just kind of use this as a point of comparison with the regression results that we just got. So I'm going to click on OK. And for starters, notice that when we're looking at our output from the original regression results, you'll notice first off that we have the R-square value, it's 0.949, and the adjusted R-square is 0.947. You'll see the ANOVA F and the p-value right here. Now, if we look down below in the output for the univariate analysis of variance, you'll notice that we get our F value, which is exactly the same as this. Our p-value is exactly the same. You'll notice that we get partial eta squared right here, which is the R-square value that you get from the model summary table above. You also notice that below in the table, you'll see it says R square, which is the eta squared value right here, and you'll see the adjusted R square, which is the same as what we had above in the ANOVA summary table. So it's all exactly the same, and in fact, when you look at the degrees of freedom for the correct model, this is equal to the number of predictors that we've included in our regression analysis, and then you can see the degrees of freedom error is 45. So if we go back up and look at our previous ANOVA summary table, you'll see we had, from the regression, we had 2 and 45 right there, and then your total degrees of freedom is 47, so which is this right here. So if we scroll down a little bit further, you'll notice that with the parameter estimates, all of this is exactly the same. So you'll see that we have self-efficacy and worry, and we even get our confidence intervals right here. And as you're looking at what we generated previously, these are the same values for our regression coefficients, the standard errors. Now we're not getting the standardized regression weights in this table, so that would be one limitation. So if you wanted those, you'd have to run it through the other option. But nevertheless, you can see the confidence intervals are exactly the same as we saw above. Moreover, when you're looking at the partial eta squared values that we have right here, oh, and by the way, the intercept and all that information is exactly the same as well, so I did want to just point that out. But the partial eta squared values are nothing more than essentially the square of the partial correlation. So I actually generated the partial correlations, basically between each of the independent variables and the dependent variable interest. And so if you essentially, if you square, let me just kind of go back here. If you square the 0.741, you get the 0.549. If you square the negative 0.598, you get the 0.357. So so if you wanted to report in terms of partial eta squared, you could certainly do that. It's just basically the square of the partial correlation above. Now, if you want to test your residuals for heteroskedasticity, you might still want to go through and look at residuals plots and so forth. But you can also, now if you go under options, you can also carry out various heteroskedasticity tests. So you have essentially the Broch-Pagan test, modified test, and also F-test. And then there's a more general test, which is White's test. And basically the way that you do this is you'll click on Model and click on Use Univariate Model. And so it's just going to be based off of these predictors that are included. So I'm going to click on Continue. I'll do the same right here. And I'll even do the same right here, and click on and then so if there was a situation where I decide that there is a violation of the assumption of constant variance, then I could also, one of the nice things through this approach is I could also generate regression results using heteroskedasticity consistent standard errors. So and so the default is the HC3 right here. And so I'm just going to go ahead and generate that, even though I've already run this and there's not any real evidence of heteroskedasticity. So I'll click on OK. And so now you'll see that we have, here's a White's test right here, and there's our p-value. So, and the null hypothesis for all of these tests is constant variance. So if you reject the null hypothesis, then you're essentially adopting the decision that we have a violation of the constant variance assumption. So in each of these cases, all of these values, the p-values are greater than 0.05. Which are basically indicating that we're not really having any problem with constant variance, with heteroskedasticity in terms of the residuals. But you can see down here we have again our OLS results, which we generated just in the last demonstration. But now we have parameter estimates with robust standard errors. So you'll notice that all of our regression coefficients are going to be exactly the same. The difference lies in the standard errors that are used. So you can see right here we have adjusted standard errors relative to what we had before. So these are the OLS results, with the standard errors that are generated, and then these right here are the the standard errors using the HC3 approach. So you'll notice then that that here are our t-values before and our t-values afterwards, and you can see the confidence intervals look a little bit different as a result. But nevertheless, it didn't appear that we violated the assumption, so there's not really much need to utilize these test results right here and we can just kind of utilize our standard results. But the really great thing about the options tab under this general linear model univariate approach is that we are actually able to carry out tests for heteroskedasticity, and then if there's evidence of a violation of the constant variance assumption, then we could actually go ahead and carry out our regression analysis using adjusted standard errors. If you want to, just for comparison's sake, there's a nice little macro at this particular website right here. And if you download it, it's not on the screen right here, but you can actually download the macro, and I think this is the most recent one right here. If you download it and run your analysis through it, this is it right here. I'm going to go ahead and ask for HC3 as well, but then you can see right here that when we're looking at our tests, you can see the BP right here. This is the Bruch-Pagan, and that is the original. Those are the values from the original test. So that's the 1.595, and if we scroll up here, you'll notice that we have our chi-square value of 1.595. There's the significance level. It's the same. And then this one right here, this is the Cohenker test. I think I'm pronouncing it right. I hope so. And the p-value right here, so it's 2.084. If we look down here in our test results, you'll see that there's a 2.084 and the p-value, which is exactly the same as above. You'll also notice that right here you can see that with this test we have the OLS output right here with the standard errors, and then we have the adjusted standard errors using the HC3 approach, and so those are exactly the same as above. So basically we're pretty much able to get the same results as what we get on this using this macro if we just go through this option right here, and again use the options tab. So at any rate, that pretty well concludes this particular demonstration, and hope you find it useful.